Here we are, first video of a new unit. It's always such an exciting time, such promise and excitement of what the future holds. So unit 2 is going to spend a lot of time looking at distributions, all right? Today we're going to just talk about distributions sort of in general, but then we're going to spend the back half of the unit focusing on the normal distribution, right? So the big topic from this is going to be the normal distribution. And again, this unit won't be as long as the first one. That first one is probably one of the longest units that we do in the year. Okay, so today's topic is describing location in a distribution. So you have a distribution of data. How do you describe where various points fall in that distribution? So one way to do that is a percentile. So what's a percentile? All right, you've probably heard these before, like when you get like test results back, like, oh, your test score was in the 98th percentile, or if you're not that smart, your test score was like in the 3rd percentile. I joke. I'm sure you all tried your hardest. All right, so percentile. I'm going to use the letter P because it's percentile. The Pth percentile, so again, that could be 99th, 87th, 23rd, whatever percentile of a distribution is the value with P%, so whatever that original percentile was, of the observations are less than that value. And notice that I didn't say less than or equal to, I said less than, and that was on purpose. So it is the value with which, P% of the observations are less than that value. All right, so if I wanted to, so we've got an example here, right? So here's test scores. We've got 25 test scores, and they're in numerical order. If we wanted to find the percentile for the score of 72, right? Here's 72. What we're really asking is how many observations are less than that value. Okay, so here we have one observation less than this value. There are 25 observations in total. So there's one less than it. So that would be 1 over 25, which would be 0.04. All right. Or you could think of that as 4%. Or you could think of that as the 4th percentile. All right. So a score of 72 is at the 4th percentile because 4% of the observations are below that value. All right. If we were to find the percentile for 93, right? 93 is our highest value actually in this distribution. Right? There are 24 observations less than that. Out of the 25 observations, so that would be 0.96 or 96% or the 96th percentile. So 96% of the observations are below that value, and then they can be anywhere in between. So find the percentile for 80. All right, so here's 80. It doesn't matter that there's 2 of them because we're counting the observations below that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 out of 25, which is 0.48, which equals 48%, or the 48th percentile. All right. Now, you might be saying to yourself, well, if we're always doing less than, then it's impossible to be at the 100th percentile. And yes, that's true. But do note that there are different ways of calculating the percentile. You can do less than or equal to. Sorry, that's the programming way of writing less than or equal to. You can do less than or equal to for percentiles. It's just important that you sort of define which way you're doing it. But to keep things simple in this class, we're just going to stick with less than. So anytime I ask you to calculate a percentile, we're going with the less than definition. All right, they can be defined with a less than or equal to definition, but we're not going to use that definition. All right, so we are going to do the less than definition. And yes, that prevents us from ever having something at the 100th percentile, but also realize that a lot of times when you're doing percentiles, there's like thousands and thousands and thousands of data points. So things that seem like a big deal, like less than versus less than or equal to, tend not to be a big deal when your data set's a lot larger. But when we have these like small data sets, it's like, wow, like that's a huge difference. Like one observation is 4%. Sure, when you have a small data set, but when you have a really large data set, one observation in one direction or another might more or less be insignificant. So you can define percentiles as less than or equal to. We're not going to in this class. We're going to stick with less than to keep it consistent. So just know that anytime I'm asking for percentile, you want to use less than, not less than or equal to. Now, you might not have been thinking about it this way, but we've already done percentiles a little bit, all right? Q1 is the 25th percentile because 25% of the data is below Q1, right? The median is your 50th percentile, all right? And then, shouldn't be surprised here, but Q3 is your 75th percentile. So we've already sort of been using percentiles. We've just been using sort of the big three sort of general ones. Now we're just extending it out to any value in our distribution, all right? We can use this to sort of figure out where we are in the distribution. And we've been doing that already with Q1, median, and Q3. And now we're just extending it so that we can see exactly where any observation falls inside of a distribution. All right, so let's go to a way to visually sort of represent these. All right, so we have the cumulative relative frequency graph, all right, also known as an ogive. This is a plot where a point corresponds to the cumulative. I'm doing that thing again where I'm using the word in the definition, but it'll make more sense when we actually do the example. Cumulative relative frequency in each class at the smallest value of the next class. So you're probably wondering what the heck that means. That's totally fair. Let's look at an example, and then it should become a little clearer. All right, so we have here data on the age of the first 44 US presidents at the time of their inauguration. So like there were 2 presidents that were between 40 and 44, 7 presidents between 45 and 49, 3 presidents between 65 and 69. So again, that's kind of what we're doing here. So the relative frequency is just basically the percentage. So like what is 2 over 44? What is 7 over 44? All right, that's just what the relative frequency is. We're just calculating the percentages for each of these. All right, and I'm not going to write these all down, but each one is a percentage. And the first one would be 4.5%. The second one would be 15.9%. The next one would be 29.5%, 27.3%, 15.9%, and 6.8%. Okay, so these are the percentages for each of those. Now, cumulative basically means that we start with our small group, and then we keep making that group bigger and bigger and bigger and bigger and bigger and bigger until eventually the group is everybody. So the cumulative age frequency, or the cumulative age range, sorry, would be 40 to 44 at the start, because that's just our first group. Then when we add the next group, we still start at 40, but now we go up to 49. And then we still start at 40, but now we go up to 54. Still start at 40, go to 59. Still start at 40, go to 64. Still start at 40, go up to 69. So the cumulative frequency would just be how many fall in each of these ranges. So the first range has 2. The second range, which includes the first range, is now up to 9. And then we go up to 22. And then we get another 12 on that. So that's going to bring us to 34. And then another 7 on that, which is going to bring us to 41. And then another 3 on that, which is going to bring us to 44. So when we say cumulative frequency, it's just we keep getting bigger and adding to what we already have. And then the cumulative relative frequency would just be how those percentages are changing. So the first one's still going to be 4.5%, but now we're basically doing 11 out of 44. All right, so this one would be 11 out of 44, which is going to give us, sorry, not 11, 9 out of 44. All right, I don't know why I said 11, probably because I was thinking that would be easy to do. But it's 9 out of 44, which is 20.5%. And then it would be 22 out of 44. And that one's easy. That one's just 50%. And then again, I'm not going to keep writing the fractions, but we're just adding these percentages on. So the next one would be 77.3%. The next one should be 93.2%. And here's the important part. When you get to the end, you should always be at 100%. Right? So you always get to the 100% there. All right. So if we look at our graph here, because this is the graph that's made from those values, right? It starts at 0, and the 0 is at 40. Our next range is at 45. And what we do is we have the graph go up to that 4.5% when it hits 45. And that's what this line of the definition that says where a point corresponds to the cumulative relative frequency in each class at the smallest, oh, look at that. I forgot to write the word value, of the next class. That's probably why it didn't make any sense. At the smallest value of the next class. So our class goes from 40 to 44. The next class starts at 45. And that's where that 4.5% is going to, right? The cumulative frequency for the next one is 20.5%. We don't put it at the 45. We put it at the smallest value of the next class. So this 20.5% starts at 50, which is the smallest value of this class. All right. And then it just goes from there. So this 50% is for the 40 to 54 class, but the dot is going to go at the 55. So there's my 50%. And then it just keeps going from there. So the 77.3 is going to be at 60. The 93.2 is going to be at 65. And the 100% is going to be at 70, which technically we don't even have a range at 70. So the cumulative relative frequency is always plotted at the smallest value of the next highest range. So this 4.5 is plotted at 45. This 20.5 is plotted at 50, and so on and so forth. That's what this definition was trying to say up here. All right. Now, I'm not going to ask you to make these graphs very often, but what I am going to ask is your ability to read these graphs. So let's talk about how we would read one of these graphs. So if it says what percent of presidents were inaugurated before they reached the age of 60? All right, what we could do is we could say, all right, here is 60. All right, so we go straight up from 60. All right, that brings us right here. And then if we go over, that will give us the percentage. Now, we actually have that percent right here from the table, but we can read the graph by saying, oh, I want to know what's less than 60. So let me go to 60. Let me go up. Let me go over. And then my answer would be that 77.3%. And I'm only being that exact because I know it from the table right here. But you would just estimate sort of what it was from that graph. So if it says what percent of presidents were inaugurated before they reached the age of 53, all right, I'm going to estimate that 53 is about right here. I'm going to go up from 53. And then when I hit the graph, I'm then going to go over and to the left. Right now, ideally, you would have some sort of ruler here, but I'm going to say roughly 40%. Now, you can read these graphs in either direction. So this one says roughly 80% of presidents were inaugurated before they reached what age? So in that case, I would start at 80%. I would go over. I'd hit the graph, and then when I hit the graph, I would go down. All right, and I might say, I don't know, it's like 61 or 62. All right, but that's how you read one of these graphs. You either start at the percentage, go over and then down, or you start at the value and then go up and over. So you can go in either direction. You can go up and over, or you can go over and then down. And the direction that you're going is just a function of what the question is asking. All right, so this one is giving you the percent, and it wants to know what value goes with that percent. So we start at percent, go over and down. This one's giving you a value, so we start at the value, go up, and then over to calculate the percent. All right, but that's the key, is your ability to read these graphs. I'm not as concerned with making them, but I do want to make sure that you're comfortable reading one of these graphs. So there will be pretty frequent questions on that. All right. So again, it's all about sort of finding data's place in the distribution. Where in the distribution does this data fall? And again, being more granular than just quartile 1, median, quartile 3, being able to break it down and get the position of individual data values and where they fall in the distribution. All right, so another tool to figure out where things fall is the Z-score, right? And this is going to be something that we pretty much use the rest of the year. All right, so a Z-score is also known as a standardized value, and it represents the number of standard deviations that an observation falls from the mean. right? It can be positive, it can be negative, all right? So positive would mean above the mean, and negative would mean below the mean, all right? So you can end up with positives and negatives in this one, all right? So you can end up with positives and negatives, and the formula is Z equals X minus X bar divided by S of X. So you're seeing how far the observation, X is our observation, you're seeing how far the observation is from the mean, and then you're dividing that by the standard deviation so that you can see how many standard deviations the observation is from the mean. All right, and the Z-score is useful because it allows us to compare values from different distributions. All right, sometimes you say, oh, we can't compare those things. They're apples and oranges. The Z-score tries to turn everything into an apple. All right, it tries to make it that even if things are from different groups or from different eras, we'll still be able to compare them through the use of this Z-score. And we'll see a couple of examples on how that works. Another thing to note is that because the Z-scores are based on the mean and the standard deviation, it's important that the distribution is fairly symmetric. So that's one of those lessons we learned in the first unit, is that you don't want to be using means and standard deviations if the distribution is skewed. The same is going to apply here. Right? These are based on mean and standard deviation, so we want a fairly symmetric distribution. Whereas we don't have that same concern with the percentiles. Right? So we're still seeing sort of this dividing line between what we do for symmetric distributions and what we do for skewed distributions. All right, so let's actually take a look at an example here. Imagine a brother and a sister took the geometry and trig regions, which is also algebra 2. I just keep calling it trig because I can't let go. At the same time, both distributions are fairly symmetric. If Susan earns an 86 on the geometry regions and Connor earns an 82 on the trig regions, who should receive more of their parents' love? All right, so this is the type of question a Z-score can answer. So Connor scored an 82 when the average score, Susan scored an 86 when the average score was an 80. Connor scored an 82 when the average score was a 76. So you might be saying, well, they both scored 6 points above the mean, so they did the same. But that's not really true. All right, standard deviation sort of reflects how impressive being 6 points above the mean actually is. And here's the quick example that I like to do. All right, imagine if you have a class where the test average was, we'll say, 90. All right, so the test average was an easy test. The test average was 90. All right. Well, we could have a bunch of 100s. And we could have, 1, 2, 3, a bunch of 80s. Right? Right? That will average out to 90. All right, there are 6 100s. There are 6 80s. That will average out to 100. Right? And most of those observations are about 10 away from the mean. So it would be a standard deviation of about 10. All right, not exactly, but it would be about 10 because most of these observations are 10 from the mean. And we know that standard deviation is the average distance from the mean. Now, compare that to a different class, right? The test average is still 90, but instead of a bunch of 100s and a bunch of 80s, we got a whole bunch of 90s, and then maybe there's one person that got a 100, and there's one person that got an 80. All right? the standard deviation for this class is going to be a lot lower. And I think if most people looked at it, they would intuitively say, oh, this 100 is more impressive than these hundreds up here because only one person got it here, and lots of people got it here. But in both cases, the 100 is 10 points above the average. So it's not enough just to look at the distance from the average. We also need to know how spread out the data is. And without that information, we can't really assess how impressive it is to be 10 points above the average. And that's why the Z-score doesn't just look at the distance from the mean. It puts it in the context of how spread out is the data. So if we look at geometry here, we got 86 subtracted by 80 divided by 6, or 6 over 6, or put another way, 1 standard deviation above the mean. All right, so that score of an 86, yes, it was 6 points above the mean, but more relevant is 1 standard deviation above the mean, because how spread out things are reflects how impressive it is to be 6 points above the mean. All right, so over here on trig, we've got 82 minus 76 divided by 4. Again, 6 points above the mean, but the standard deviation is 4, so it's less spread out. It's more it's more similar to this situation right here. And 6 divided by 4 is 1.5 standard deviations above the mean. All right. So even though Connor's score is lower, even though Connor's score is lower, it can be considered more exceptional than Susan's because it is more standard deviations above the mean. Okay? So this gives us an idea of how unusual, how exceptional, how far above the average does a value fall, and it sort of standardizes it by looking at the makeup of the distribution and using that to put sort of things on equal footing. All right, it's not just 6 points, 6 points. It's 6 points when this is how spread out things are. It's 6 points when this is how spread out things are, and it gives us a way to compare things across different distributions. Now, what units should Z-scores have? Well, if we look at the calculation, it was 86 points minus 80 points divided by 6 points, because standard deviation has the same unit as mean. All right, so mean and standard deviation, standard deviation have the same units. So that means we ended up with 6 points over 6 points. Or put another way, this cancels out. You're just left with 1. And we can basically say that Z-scores are unitless. Right? They do not have a unit. It's technically a standard deviation, but a standard deviation isn't a unit. So it's not, we can't say like, oh, the unit is standard deviations. Yes, it's referring to standard deviations. This is 1 standard deviation above the mean. But standard deviation isn't a unit the way centimeters are a unit, or the way points are a unit, or the way feet are a unit. It's more of like a label, like that represents one standard deviation. It's a way of talking about it, but it doesn't have a unit. And this is one of the advantages, and this is what allows us to compare things, is that they're unitless. So by removing units, it gives us this equal footing for comparison. All right, but we would never say, oh, the z-score is 1 inch or 2.5 meters or 1.7 seconds. All right, z-scores are unitless. We just say, all right, the z-score is 1 or the z-score is 2.5. You can say it's 2.5 standard deviations. That's fine, but just don't put any sort of units on it. All right, last but not least, let's just do another example. All right, scoring a decathlon. So decathlon is an event in track where there's a whole bunch of events, and you get points for how you do in the different events. But fundamentally, those 10 events are condensed down into one competition. There's only one winner. So how do we really compare things when they're totally different events? You know, we're simplifying it down to 3, but like 100-meter dash, shot put, long jump. They're all measured in different things, yet somehow we need one score to encapsulate somebody's performance. All right, so one way we could do that is with z-scores. All right, z-scores allow us to sort of compare things that are part of different distributions with different units. So let's say we wanted to see how competitor A really did overall. All right, we could say, all right, for competitor A, let me put competitor A here. I want to know how they did in the 100-meter. I want to know how they did in the shot put. And I want to know how they did in the long jump. So I could calculate a z-score for each of their performances. Right? So I could say, oh, they did a 10.1 in the 100-meter dash. The mean was a 10, and the standard deviation was 0.2. Now, this is where you have to just know a little something about running, and not a lot. It's pretty clear, but like in running, having a low time is good. You know, in most sports, you want to have higher scores, but in running, like obviously you want your time to be lower, because lower means faster, which means you won the race. So if we did this calculation the way that it is, 10.1 minus 10, we'd get a positive number, which would generally suggest that you're above average. But in running, you actually want the lower numbers. So what we're going to do is we're going to negate our result here to sort of flip the sign. Because otherwise, we're going to say that 10.1 is a good thing when really you're slower than average, and that's a bad thing. All right, so if you type this in your calculator, you're going to get 0.1 over 0.2, or put another way, you're going to get 0.5 because you 1 over 2. So this works out to be negative 0.5. Now, shot put is more straightforward because that one is just the longer the better. So we don't have to negate anything here. We can just do 66 minus 60 divided by 3. Again, observation minus mean divided by standard deviation. And we get a value of 2. And then for long jump, all right, we can say, all right, this is 26 minus an average of 26 divided by a standard deviation of 6, but 26 minus 26 is going to be 0. So we've just got that. So if we take this in totality, we can say, oh, they were half a standard deviation below average for the 100-meter dash. They were 2 standard deviations above average for the shot put. They were perfectly average for the long jump. So if we wanted to combine all of these together, because now remember the units have been erased, we could say, oh, competitor A was 1.5 standard deviations above the averages across all 3 events. Right? And then we could do the same thing for B to see which athlete was truly more exceptional. So B was 9.9 minus 10 over 0.2. And again, because this is the running one, we have to negate it so that when you're faster than average, you end up with a positive z-score of 0.5. Right? For the shot put, B was 60. So that would be 60 minus 60 divided by 3, or 0 divided by 3, or 0. And then for the long jump, B was 27. All right, minus 26 divided by, and as I do this, I realize that I made a mistake on A, but thankfully it didn't really hurt us because it was 0. So the standard deviation is actually 6 inches, not 6 feet. And 6 inches is half a foot. So I should have actually been dividing by 0.5 here. So I apologize for that. But this is 6 inches. 6 inches out of 12 inches in a foot tells us that this is half a foot. So we should have been dividing by 0.5, which means here we're also dividing by 0.5. 6 inches, half a foot. So 1 divided by 0.5 is going to be 2. And then if we sum all these together, we can see that athlete B was 2.5 standard deviations above the mean across all 3 events. So we can already see that competitor B was superior to competitor A, even though they each won a single event. Like, all right, B won this one, A won this one, and C won this one. So they all won a single event. But if we look at everything in totality, we can see that, oh, overall, B was more impressive than A. All right, and now let's see how C stacks up. So for C, we've got 10.3 minus 10 divided by 0.2. And again, this is one where we're going to flip it around because slower is bad. All right, so that works out to be negative 1.5. For the shot put, it was 63. So 63 minus 60 divided by 3. And that gives us 1. And then on this last one, we have to be careful. This is 27 feet 3 inches. 3 out of 12 is 0.25. So we can write that as 27.25 minus the mean of 26 divided by, again, that's 6 inches. So 0.5. All right, so effectively we're doing 1.25 divided by 0.5, which works out to be 2.5. And then when we add these all together, 2.5 plus 1.5 is 3.5, but then we're subtracting 1.5. So that brings us down to 2 standard deviations. So even though these 3 competitors all won a single event, by looking at z-scores, we can sort of look at their performances all together and conclude that our overall winner should be B. All right, so gold, silver, bronze. All right, but again, we can only do this by stripping the units from these things, by calculating z-scores so that we can then sort of compare everything across a single metric there. All right, so again, this is the advantage of z-scores, is it lets us make these comparisons. All right, so that is it for today. I hope this was useful, and I will see you when I see you. Bye.